Okay, so I'm going to give this talk on simulations. And the idea is, why do we need simulations? What is simulations and how to use them? So before we start, I would like to start with a movie clip. This is from YouTube. Let me run it first. So this was a clip from the movie Apollo 13. And the person who was woken up at night was basically an astronaut. He was by training he was an aeronautical engineer. He was also a test pilot, and then he became an astronaut in NASA. His name is Ken Mattingly. His picture you can see here. Now, he was chosen as the command module pilot on the Apollo 13 mission in 1970. And exactly 3 days prior to the launch, he was removed from the mission due to exposure to German missiles, which actually never contracted, but there was a risk, so he was removed. And then he was replaced by a member of the backup group. As a result, of course, he was not very happy. He had to stay back on Earth while his colleagues went on to the space. But in a way, it was good because for him it was good because there was an explosion in Apollo 13, so he didn't have to go through this explosion. And this explosion apparently, crippled the aircraft, the spacecraft. And also, it was good. It was a blessing in disguise because Ken was actually the engineer who had built that engine for that spacecraft. So he was called at night, as you could see in the movie. He was called at night, and then he was asked to help out in the situation. And he played a very important role in helping out the crew who were going through distress because of the accident. The thing that he helped with was he helped them to solve the problem of power conservation during re-entry through simulations. So as you could see, he was being put in a simulator. And then he specifically mentioned, remember, give me exactly the things that they have in the spacecraft. Don't give me anything that they don't have. So using these, all the stuff that astronauts had in Apollo 13, he was trying to just imitate the situation in Apollo 13, and he was trying to help them to conserve power during re-entry. Now, this is absolutely important because when a spacecraft enters the Earth, it has to perform various things exactly in the right time at the right point so that they can enter, the heat shield works, and they can enter the right angle, exactly the angle that they want to enter. And for that, of course, the spacecraft needs some power, and power was a problem for Apollo 13. So Ken Mattingly, what he did, he simulated the situation and then prescribed a procedure that will help them save power. You will just do some maneuvers, like certain things that are not necessary, he won't start, etc. By doing this maneuver, he suggested or prescribed a method that would eventually save this spacecraft. And the Apollo 13, as you perhaps know, came back to Earth, and the astronauts are alive. So the key thing was the simulation that was done. So, and this is 1970, as you could see. In 1970s also, for NASA, for space missions, simulation was so important. This was a very specific example, but of course, simulation even saved lives. Now, what is simulation? So, according to Wikipedia, simulation means imitation of the operation of a real-world process or systems over time. simulation require the use of models. The model represents the key characteristics or behaviors of the selected system or process. Whereas the simulation represents the evolution of this model over time. Often, we need to use computers to execute simulation. So this is what Wikipedia says. So therefore, why is it important? Why is simulation important? As I already mentioned, it's an imitation of a real-world process. So in the example that we already saw, in the Apollo 13 example, there, the real-world process was the aircraft which was coming back to Earth. And Ken Mattingly was just trying to imitate that in the NASA laboratory, using some machines that can be called the model for the spacecraft. So models are extremely important because in order to imitate the real world phenomena, we need a model. Now, why is it important? So as you can understand, it helps us understand the evolution of the real world process that we are trying to imitate. It's absolutely important to do that. In many cases, it also helps us improve the system and its dynamics. One crucial example in this respect would be the self-driven cars. These days, as you know, using artificial intelligence, people are designing self-driven cars. And then it has to go through various simulations. And then many cases it will fail for various reasons. And the simulation will show exactly for what reason it failed. And then it will be improved thereafter. So therefore, improvement is also a very important contribution of simulations. As a result, simulations are useful in science, engineering, banking, insurance, etc. There are various. The field of applications is very, very, very broad. Now here is an example. Now this example is from science. It's actually from botany. So in by the way, this image is due to Jon Evans. In 1827, Scottish botanist Robert Brown was examining pollen grains suspended in water. And he was examining them under a microscope. What Professor Brown observed is that he observed some minute particles which were coming out of the pollen grains. They were executing a continuous jittery motion, always moving like this. Brown could not provide a theory to explain what was going on in this phenomenon. Later on, other scientists did that. I'll mention briefly now. But since it was first observed by Robert Brown, this jittery motion or this phenomenon is now known as Brownian motion. One thing that he observed, though, was that this motion was not the motion of the pollen grains. By doing various experiments, he realized that the pollen grains are moving in this jittery motion because of the particles in the water moving continuously. This is something he observed himself by using various chemicals instead of pollen grains. In 1905, so this was, as you can see, this was after like more than 75 years, almost 80 years after the first observation by Robert Brown, theoretical physicist, world-famous theoretical physicist Albert Einstein published a paper where he modeled this motion of pollen particles as being moved by individual water molecules. So Robert Brown's observation was correct. So this was not the motion of pollen grains, but pollen grains were getting this motion. It was a motion of pollen grains, but pollen grains were getting this motion from the motion of the water particles, the water molecules. Now, this 1905 paper is definitely one of the most famous papers that Albert Einstein wrote. He wrote a few very important papers, right? One was on photoelectric effect, which gave him a Nobel Prize. And then he wrote a paper on general relativity. He wrote another paper on special relativity, and also this paper on Brownian motion. If somebody asks what are the 4 important papers written by Einstein, I would at least answer that these are the 4 most important papers, Brownian motion being one of them. Brownian motion, as you can expect, therefore, arises naturally in physics, in chemistry. It also arises in biology, and even in the analysis of financial market. Now, let's go to this Wikipedia page once to see how this Brownian motion looks. Okay, this jittery motion looks. Let me just, okay. So I'll click on this. So here you see there are 5 particles which are moving and making this jittery motion, and the path of the particles you can see as these blue lines that are here. And these blue lines represent the paths of each of the particles. As you can see, they are very jittery. These paths are very jittery. And then this path, they are getting this path because of continuous movements of the molecules of water, which is simulated here, which is shown here using these black dots. So these black dots are the molecules, and they're these yellow ones are pollen grains. They're continuously, getting and then it has to make stop this. Now, please translate this. Okay, so we will answer this question slightly later, not at the beginning of this talk. This is a very difficult example in some sense. What we will do, we'll start with some very simple examples that we may face in everyday life. From there, we'll go on to how to simulate Brownian motion. Okay, so as I said, we'll start with some easy examples. So let us try to answer a much simpler question. The question is the following. Suppose you have 2 people, say two students, out of which you have to choose one at random. When I say at random, I mean I have to choose one with equal probability. So I won't do any favoritism. I'll choose either A with probability 50% or B with probability 50%. Question is how to do that. This can happen in various ways. For example, you may have to choose between 2 siblings and then send one of them to market, and then you want to be fair to both of them, and then you just have to choose one of them with 50%. Both of them should get 50% chance. Now, of course, the way we would do it in real life is we'll take a coin and toss it. If head appears, we'll choose the person A. And if tail appears, we'll choose the person B. That's a natural thing to do. Now, under this, for this, we need an underlying assumption. We are always tacitly assuming that the coin is fair, in the sense that the coin is unbiased towards both head and tail. So in the probability of getting a head in a toss is 50%, and probability of getting a tail in the toss is also 50%. So this is what we are assuming. If that is indeed the case, in other words, if the coin is indeed fair, then of course we will get this. When we use this method, we'll choose A with probability half, and we'll choose B with probability half. But the question remains, what if the coin is not fair? And let me tell you this, most of the coins that we use, they are actually not fair. They have a bias either towards the head side or towards the tail side. So even though we assume in many problems that the coin is fair, but in many cases they are not. The question is, how are you going to simulate this event that you have to choose probability A with probability half and B with probability half using a possibly unfair coin? So here is the question. So basically we're asking, using a possibly unfair coin, how can I simulate an event whose probability is 50%? Okay, this is what we are asking now. Now there is a way to do it, even if the coin is unfair. Okay, so what do we do? Instead of tossing the coin once, you toss the coin 2 times. Okay. If you get both heads or both tails, then reject this outcome and go back to step 1, which means you toss the coin again 2 times. If not, that means if both are not same, both outcomes are not same, then of course you either got head followed by tail or tail followed by head, which I'm representing here by HT and TH respectively. Then you do the following. If HT appears, then you choose A. And if TH appears, then you choose B. So what we do is we assume tacitly that the 2 tosses are independent. In other words, the outcome of one toss does not influence the outcome of the other toss. So they are, free of each other. The outcomes they don't depend on each other. If that assumption is correct, which is not a bad assumption to make, then what happens is this HT and TH, these are the only 2 accepted outcomes, right? Because if it's HH or TT, we reject the outcomes and then we toss it again. So we go on tossing till we get either HT or TH. So the only possible outcomes are, in the end, the only possible accepted outcomes is either HT or TH. And they are both equally likely. Probability of HT and TH are equal. Therefore, this method is going to work. Eventually, you will get either HT or TH. And then the moment you get it, if you get HT, you get HT with probability 50%, and you get TH with probability 50%. So therefore, you're choosing A with probability 50% and choosing B with probability 50%. So therefore, using a coin, which you don't know whether it's fair or not, you can use this method to simulate a probability whose chance is, an event whose probability is 50%. Now, suppose I complicate the problem a little bit more. Now, you have to choose one person at random with equal probability out of 3 people. Let's call them A, B, and C. How can you do that? Using a possibly unfair coin. In other words, I'm asking the following question. Using a possibly unfair coin, how can one simulate an event whose probability is 1 over 3? Now, this method is called acceptance-rejection method. So I already told you the simplest possible application of that. Now this is the next step. So what you do, and I'll tell you why it's called acceptance-rejection method. What you do now you have to choose 1 out of 3 people. So now you toss the coin 3 times. Okay. if HHH or TTT appear, then reject the outcome and go back to step 1, which means if all the tosses give the same outcome, then you just reject the outcome and you go back to step 1 and then again toss the coin 3 times. I would like to stress that here also we are assuming that the 3 tosses that we are doing are independent. They don't influence each other. Now, suppose you don't get HHH or TTT. Okay, not all heads or all tails. Then, of course, you will get one of these 6, right? There are only, if you toss a coin 3 times, there are only 8 possible outcomes. So you will get one of these outcomes for sure. Then here is the method of choosing A, B, C, one of A, B, C at random. If THH or HTT appears, then choose A. If HTH or THT appears, then choose B. If HHT or TTH appears, then choose C. Okay, so I would like to stress one thing is that I have given this very specifically, I've written them also very specifically for A, B, and C. Like why? Why have I done that? Last time, let's go back quickly. Last time, what we did. Last time, if HT appeared, we chose A. If TH appeared, we chose B. And this is because HT and TH are equal in probability. So the probability that HT appears is same as the probability that TH appears. Here also we are doing the same thing. We are making sure the probability of this event is equal to the probability of this event, and that's also equal to the probability of this event. And the way we are ensuring it, I've written in as 2 columns, right? This column, if you see, all of these events have equal probability. It's exactly 1 tail and 2 heads. Depending on where the position of the tail is, you choose the event. You put the event in A, B, or C. All of them have the same probability of occurrence. Similarly, these 3 that I have written in 1 column, they also have same probability of occurrence. So in particular, this means that this A, B, and C will be chosen with equal probability. And of course, HHH and TTT is out of the list. So the only accepted outcomes are these 6, out of which I'm breaking them into 3 groups in such a way that the probability of each group is 1/3. The probability of each group are equal. Okay, so therefore we'll choose A, B, C with equal probability. So it's the same method that last time it happened. So last time it happened with 2 out of 2 people have to choose 1. Here we are choosing 1 out of 3, and then we have to toss it 3 times. Now you see why it's called acceptance rejection method. Because depending on the outcome, we are rejecting some of the outcomes. This is the rejection step. And then finally, we are accepting one of the, all the other outcomes. And depending on what the outcome is, we are giving an output, A, B, and C. So we are doing both rejection and acceptance, finally acceptance. So that's why this is called acceptance rejection. Okay, so when I get the talk there, some questions were asked. Maybe I'll discuss these questions that were asked here right now before moving on. Okay, so one of the questions that was asked was, will I be able to choose one person at random from a group of any number of people? And the answer is yes. So that's what I'm going to, I wrote down next. So this acceptance rejection method can be used to choose one person uniformly at random from a group of any number of people. So for example, if you have a group of 100 people, you just have to toss the coin 100 times, and then you can give a method. The method may not be as simple as the way I have done it for 2 or 3, It may be a little bit more complicated. You have to make sure the events that you are assigning to each person, for choice of each person, in the acceptance step, all the events have equal probability. That's something you have to ensure. But once you ensure that, this method can be used. And I would just say that this method is not just applicable in these situations where you are simulating a probability of, say, 1/3 or half or something, an event of probability 1/3 or half or something. It's actually very useful and a very popular simulation method in many, many complicated situations. Of course, what you would reject and what you would accept, that depends on the model, that depends on the situation, that depends on various factors. But the common thing is that you either accept or reject in one step. And that makes it an acceptance rejection. Okay, so let me go back and answer a few other questions that were asked during the talk. So another question that was asked is, why did I put two outcomes in each group? I could have just kept, say, I could have kept either of these. I could have just kept THH, HTH, HHT in these groups and removed these three guys. I could have done that. So in other words, I would reject, in the sense that I would reject if HHH, TTT, or any of these three appear. Okay? HTT, THT, TTH appear, I reject it. And then I accept only three outcomes: THH, HTH, and HHT. And depending on what appears, I'll choose A, B, or C. If I had done that, the simulation method would be perfect. There'll be no problem with it. You will definitely choose A, B, or C with equal probability. So that's the question that was asked. So why didn't I do that? Now, the reason I didn't do that is that in that case, I'll be rejecting a lot of outcomes, right? I'll be rejecting 5 out of 8 outcomes. So many times I'm actually end up rejecting it. And then hence the simulation will go on for a longer time. So if I use only these 3 outcomes, for example, then the expected time of completion of this method would be much longer. Similarly, I could have also kept this in the acceptance part, these 3, and rejected all of these 3 also, because these 3 are also of equal probability. However, if you do that, again, same problem will appear, same problem will occur. Your simulation would be correct. You would simulate either A, B, or C with equal probability, but the simulation algorithm, the simulation method will just go on for a longer time, which is not a nice thing to do, especially when there is a time constraint. So therefore, I tried to make it efficient, and in order to ensure efficiency, I chose it this way. In general, when you choose 1 out of, say, 100 people, you have to design the algorithm in such a way that 1, it should be correct, so that all the outcomes that you do for each person, all the outcomes that you assign in the acceptance portion for each person should be equally probable. And you should do it in an efficient way so that your simulation doesn't run for a very long time. Okay, so let me now move on. So now that we have discussed some of the real life examples that we see in real life, let's move on to look at what are called random walks. Now, why am I introducing this thing will become clear as we go along. So let me first introduce this model, and then I'll tell you why this is important in simulations. So what is a random walk? Suppose a completely crazy person is walking on the street. How would he or she walk? It's a model for that in some sense. More precisely, suppose this crazy person is walking on the integer line, okay, which is drawn here. This person starts his or her journey at the point 0, at the number 0. And then here is the method. So if head appears, then he or she will take a step towards the +1 side. If tail appears, then he or she will take a step toward the -1 side. So perhaps I mentioned this, but he or she is tossing a fair coin. So I should have mentioned that first. So this crazy person has a fair coin, and he or she is tossing that fair coin. If head appears in that coin tossing, he or she is moving to +1. If tail appears, then he or she is moving towards -1. First, say head appears. Then this person takes a +1 step, so moves to 1. From 1, the person repeats this step. Namely, he or she tosses a coin. If the coin, a fair coin, so it has unbiased coin, it has probability of head and tail appearing both 50%. And if head appears, from 1, he or she will move to 2. If tail appears, from 1, he or she will move to 0. So in other words, head will imply a +1 step and tail will imply a -1 step. Okay. So suppose again head appears. So from 1, this person moved to 2. Now from 2, the same thing would be done. In other words, if head appears, so toss a coin or toss the fair coin. And if head appears, move to 3. If tail appears, move to 1. So in this case, perhaps tail appears. Assume the tail appears. And from 2, this person moved to 1. Now suppose again head appears. So then from 1, the person moved to 2 because it's a +1 step. Now suppose tail appears. Then from 2, the person moved to 1. Now suppose again another tail appears. So from 1, this person moved to 0. Suppose again the tail appears in the toss. So then from 0, the person takes a -1 step, which puts him or her at -1. Now suppose again another tail appears, then the person will move to -2. And this will go on. If this goes on, this produces what is called a random walk. So at each point, wherever this person is, he or she is tossing a coin. If head appears, he or she is taking a step towards the +1 side. If tail appears, he or she is taking a step towards the -1 side. So this is called simple random walk. So this is the method or the dynamics. Start at 0, toss a fair coin. If head appears, then take a step +1. If tail appears, then take a step -1. Toss a fair coin in an independent fashion. Remember, last time also independence was a very crucial assumption. Here also, we are going to assume that all the coin tosses, they do not influence each other. They're all independent. After tossing this coin, if head appears, again, take a +1 step. If tail appears, take a -1 step. And then you keep on repeating these steps 4 and 5 again and again. This gives rise to a simple random walk. And it's a random walk because this walk is completely random. Where you are depends on the outcome of the tosses, which is random. And it's called simple because every time you are taking only one step, either +1 or -1, right? So you're only taking a step of size 1, either on the positive side or on the negative side. And that also you're doing with equal probability. That is why it's simple. It's the simplest possible random walk. So that's why it's called simple random walk. So during the question answer session, there were some questions asked. I'll go back and here and I'll answer them. So then somebody first asked that what is an example of a non-simple random walk? And then I gave two examples. One is that your coin, if your coin is not, so it's called simple for two reasons. One is that every time you're taking a one step, like either +1 or -1. You're either going one step towards taking a step of size 1 towards the positive side or negative side. And also you're doing it with equal probability. So one example of non-simple random walk would be when your coin is not fair. Say your coin has a bias towards head. Okay. 60% of the time, the coin produces head. 40% of the time, the coin produces tail. Then every time the person will move towards the +1 side with probability 60% and towards the -1 side with probability 40%. Okay. So obviously the person will have a bias towards the +1 side. Such an example is called a biased random walk because it's not unbiased anymore towards the +1 and -1. This is an example of a non-simple random walk. Another example would be, so this here, the simplicity of the random walk is violated because of the coin not being fair. There is a bias towards one of the side, and hence it doesn't remain, simple anymore. It becomes a biased random. Another way of making it non-simple would be, say you don't move to 1 or -1 all the time. You move to say 1, -1, -2, or +2, all of them with equal probability. So you either take a step 1 on the positive direction or negative direction, or you take a step of size 2 in the positive direction or negative direction. So there are 4 possibilities. You do all of these 4 possibilities with probability 1/4. If you do that, then you are performing a non-simple random walk because you are allowing step sizes to be 2. So here, the simplicity of the random walk is violated because of the step size not remaining 1 anymore. It can become 2, either in the positive side or negative side. So that's why this is a non-simple random. Now, another question was asked that is it possible that the random walk stays put in a position? The answer is yes, which means, okay, let me rephrase the question. At the beginning, remember, let me show you this here. At the beginning, this was 0. From 0, this person moved to either +1 or -1. In this case, it was head, so it moved to +1. Is it okay for the person to just stay put for some time? And the answer is yes. Such a random walk is called a lazy random walk. So think of this person who is crazy, also lazy. Okay. So sometimes this person decides just to stay back wherever he or she is. So it can be happening like this. So with 1/3 probability, the person stays back wherever he or she is. With 1/3 probability, he or she moves to +1. And with 1/3 probability, he or she moves to -1. Every time. At every step. If that happens, then this is called a lazy random walk. So the answer to the question is yes. It is possible that the random walk can stay put at its wherever it is. Okay, so then this explains what is a simple random walk. Now let me quickly show you as a movie how it looks. So earlier I was doing it slowly, now I'll do it fast. If you do it fast, this is how this looks. Now we are going to represent this random walk in a graphical manner. Using a graph, we are going to represent this random walk. Now, how are we going to do that? What we are going to do is we have 2 axes. We're going to plot the time. By the way, here you can think of number of tosses as the discrete time. Okay, say you are tossing the coin at every second or every minute. So you toss the coin in the first minute. You toss the second coin in the second minute and then make a movement. Then toss the third coin at the third minute and so on. You can think of it as units of time. So every toss represents a unit of time. It can be minute, it can be whatever. It depends on the scale of the time. But you plot the time or the number of tosses of the coin in the horizontal axis. In the vertical axis, you represent the position of the crazy person. So in other words, on which integer is the person standing at that time after so many tosses. That's what you are plotting on the vertical axis. Let's take an example. Suppose the toss is done 4 times independently. So there are 4 tosses. The first one was tail, followed by a head, another head, and then a tail. If this is the outcome, then of course, from 0, the person will move to -1. So this is represented here. So see, these blue points are the representing the time and position at the same time. So the horizontal coordinate of these blue points is representing the time, okay, as shown here. And the vertical coordinate of these two ones are representing position. So at time 0, which is the start of the procedure, start of this dynamics, this person is at position 0. So therefore, we start from 0, 0, which is the origin. Then at time 1, this person, because of the first toss being a tail, the person has moved to -1. Okay, so this is the position axis. So the person has moved to -1. So therefore, we are plotting this point 1, -1, which is this point, this blue point here. Then from tail, now you have a head. Head means from -1, the person will move to 0 at time 2. So therefore, we are plotting the point 2, 0. So at time 2, the position is 0. So we are plotting the point 2, 0. Again, there is a head. So at time 3, the person has moved to 1, +1. So we're plotting the point 3, 1. Okay. And from there, again, there is a tail. So the person is going to come back to 0. So therefore, we are plotting the point 4, 0. We are plotting these points. Each point represents both the time and position of this party, of this person. Okay. Now what we are doing, these blue points, we are joining them by this light blue lines. So these deep blue particles, these deep blue points that we have plotted in the graph, we're joining them using this light blue lines. This is how we are going to represent the random walk. At one shot, we are representing the time as well as the position. So in other words, I'm just giving the entire dynamics. From time 0, where did the person go at time 1? You can see this graph and say, oh, this person went to -1. Where was this person at time 3? You will say at time 3, this is time 1, time 2, time 3. Okay, this person was at position 1 at time 3. Okay. All kinds of questions like this can be answered. For example, how many +1 steps did it take in this, in this dynamics? The dynamics meaning up to 4 steps. Well, there were 2 +1 steps. One is this one, another is this one. Other 2 were -1 steps. So the person took exactly 2 +1 steps and 2 -1 steps. All kinds of questions like this can be answered from this graphical representation of the random. Now, at this point, somebody asked me, why am I joining these points using these lines? And the answer is that, of course, the question that he or she asked is this. So whether, there is no movement of the person between time 0 and time 1, then why am I joining it using a line? Which I thought was a very good question. There is no reason, there is no physical reason for joining this using a line. Okay, we could have just plotted these deep blue points and left it there. So we are doing it for a reason, and we'll see that. Okay, we are just joining it for a reason. There is a reason why we are doing that. Okay. Now, how does this random walk grow? Here we showed the graph of this random walk only up to time 4. Instead of that, if I had plotted up to time 1000 or something, one thing that we could have seen is the following. If we go up to time n, we would have seen that the random walk is growing in the sense that its range is increasing. And then roughly, if we go up to time n, when n is large, say n is million, okay, then your range of this random walk, the way it's growing, would become of the order of square root of 1 million. Okay? So for large n, if we go up to time n, the random walk is expected to explode up to square root n, in the position axis. So therefore, this tells us that what we should do in order to see something nice, since it's growing like square root n in the position when you are going to time n, you should scale the time by n and the position by square root n for large values of n. Now, what do I mean by that? It sounds rather complicated. Let's try to make it a bit more precise. What do we mean by this is the following. Suppose that this is this slide and the next slide would be, I would say, the most mathematical side. Don't get scared. I'll tell you the ideas and then you will see what's going on. Suppose Sn is your position after n steps or n tosses. So you start at 0. So therefore your S0 is 0. So after 0 many tosses, your position is 0, obviously. Now, of course, S1 will be either +1 or -1, depending on whether the first toss, sorry, this should be toss, not two. Toss yields head or tail. Okay. And so on. So S2 is your position in the second toss. S3 will be your position in the third toss, and so on. Let's go back to this previous example, this one. Here, S0 is 0. S1 is -1. Okay. So when I say the position after the first toss, I mean position after the first toss and the movement immediately after that. Okay. So assume that the person tosses the coin and depending on the outcome immediately moves to the point where he or she should move. So then your position S1 is -1. Then the person comes back to 0 in this example because of getting ahead. So therefore, S2 is 0. S3 is +1. S4 is 0. Okay? So what we were doing in the graphical representation is we were joining the points 0, 0, 0, 0 is 0, S0 essentially. S0 is 0, remember? 1, S1, 2, S2, and so on. So here, for example, this was 0, 0. Then this was 1, S1, right? S1 was -1, so this is 1, -1. Then this was 2, S2, 3, S3, 4, S4, and so on. Okay? So we are joining these points. So in other words, in these points, in the horizontal axis, we are increasing it by 1. From 0, it became 1, then it became 2, then it became 3, sorry, and so on. In the end, it became n. And in the vertical axis, we are taking the points to its position. Initially, it was at 0, then it was at S1, then S2, S3, and so on. So by doing that, we are essentially joining the points 0, 0, 1, S1, 2, S2, 3, S3, all the way up to n, Sn. We're joining these points by lines, the line segments. Now, by scaling differently, I mean the following. Earlier, as I said, we are joining these points 0, 0, 1, S1, 2, S2, and so on. Now, you join the points 0, 0, 1 over n, S1 over square root n, 2 over n, S2 over square root n, 3 over n, S3 over square root n, and so on. N over n, S3 over Sn over square root. So essentially, your time in the time axis, you divide each point by n, and in the vertical axis, you divide each point by square root n. That's the right thing to do, because after n steps, your random walk is sort of making, exploding all in a range of square root n. So the random walk will reach, on the average, square root n distance up in n steps. That's why you should do it like this. Now, what do we see if we do this? Let's do it, okay? So, for n equal to 10, if you do this, you will see like a graph like this. So, essentially, this is a bigger version of the graph that we already saw. We saw the graph in for n equal to 1. Right? This was n equal to 1 with steps n being, this was just 4 steps we took here. Now here we are dividing, remember, this times by n and the position by square root n. So in this graph here, we are dividing the time by 10. So that's why the time, even though we are going up to time 10, we are dividing it by 10. So our time now becomes from 0.0 to 0.1, then 0.2, 0.3, and so on. The time is moving at the scale of 0.1. Okay. Then we are dividing the position by square root of 10. If we do that, this is what we will see. Now let's do it for n equal to 50. Now you see, this is looking like that. Same thing I'm doing for n equal to 50. Now I'm simulating it. Well, I have already simulated it. I'm just showing it to you. I'm doing it for n equal to 100. For n equal to 100, this is how it would look. And you see, this is already looking jittery. It's like this, right? It's jittery from before. Now you will see the more I increase n, the picture will become more and more jittery. N equal to 200. Now you already see that it looks very jittery. N equal to 500 is even more so. I'm just doing the same thing. I'm just increasing the n. I'm just joining the points just like before. The 0, 0, 1 over n, comma, s1 over n, all the way up to n over n, comma, sn over square root n. I'm joining. Only thing is n is changing. N is 500 now. Now it's 1000. If n is 1000, this is very jittery, as you can see. And I won't go all the way, I won't go further. I'll just do one more. For n equal to 10,000, you see it's extremely jittery. Okay, so you have, it looks like it's constantly moving. And this is very similar to something we have already talked about. It's very similar to the motion of the pollen grain that Professor Robert Brown had observed. So this is what gives you why it's very similar to that observation of Professor Brown. So first thing is, as we can clearly see, as I said already, the picture of the random walk is becoming more and more jittery and as n becomes larger and larger. So this was formally proved by Norbert Wiener. So what did he prove with Norbert Wiener? He showed that the scaled picture actually becomes Brownian motion when n becomes very, very large. So I'm stating the theorem of Norbert Wiener in a very informal manner. He proved some convergence, etc., using some mathematical terms, but I want to avoid all that. I'm just saying it in a very informal manner. So what this mathematician, Professor Norbert Wiener, proved is that for very large n, this picture that you see here, you're seeing it already for 10,000, and you can see it's very much like that jittery motion that Robert Brown had observed, and this this becomes Brownian motion for large n, even as large as 10,000 will do, as you can see from the pictures. So the moral of the story is that you can actually use the theorem of Wiener to simulate Brownian motion. What we do is you first simulate a simple random walk and then scale the time by n, and simple random walk up to n steps, okay? And then scale the time by n, and the position by square root n, and then simulate the picture and get something like this. And that will be a simulation of Brownian motion. So some final remarks. So simulation is basically imitation of a real world system of phenomena. Now we have seen one example, right? So Brownian motion was a real world phenomenon, which was observed by botanist Robert Brown in 1827. And then that motion is a real world phenomenon, that jittery motion, which is now known as Brownian motion. Now we use models that represents the key characteristics or behavior of the underlying process or system. Now that motion, that was observed by Robert Brown is a real world system or the real world phenomenon. Whereas the Brownian motion and its mathematical model or mathematical structure that Einstein gave is the mathematical model, is the model that represents this real world system. Now what we do, we actually simulate this mathematical model. So whatever Einstein proposed, and then we simulate whatever Einstein, came up with in his mathematical model with the help of Wiener's theorem. Okay, that's what we do. A simulation essentially mimics the dynamics and evaluation of this model over time. And here exactly what we are doing by simulating this Brownian motion and its dynamics over time. So that's exactly what we did. And most often this is carried out with the help of computers. So obviously, if you have a mathematical model, we'll have to use computers. And what we did today, in this talk is it's not just simulation, it's a very specific name to it. It's called stochastic simulation. Why is it called stochastic simulation? The word stochastic basically means probabilistic. So the simulation used probabilistic models and then coin tossing, etc. So some random, random experiments. So using those, we did perform the simulations. So therefore, this is called stochastic simulation. And for these stochastic simulations, use of computer is absolutely necessary. Okay, thank you very much. And I'll now go back and answer some of the questions that were asked during the course of the talk. So one of the questions that was asked was, so here I said that here we can use Wiener's theorem to simulate Brownian motion. We first simulate the simple random walk and then scale time and position appropriately. One of the questions that was asked is, how do you simulate a simple random walk? And the answer is very simple. So basically what we have to do, we have to always simulate a +1 and -1 with equal probability, right? Now, of course, you can do it using tossing a coin, etc. But in using computers, how do you do that? That was the question that was asked. And that can be done very easily. So every computer program or package or anything, they have a standard function, okay, that will essentially give you an output which is generating a random number uniformly at random from 0 to 1. Okay, so it's basically generating a uniform random number from 0 to 1. Uniform meaning all numbers are equally likely to be selected. Now, what you do in the computer program, whatever is your favorite program or package you use, you just simulate this uniform random number from 0 to 1. Look at this number. If this number is between 0 and half, you take a step towards +1. If the number is from half to 1, you take a step towards -1. Now, since this is uniform, the random number is uniform, the probability of this will basically simulate taking a +1 with probability half and taking a -1 with probability half. So this is how you simulate using a computer the random walk. Okay, and you go on doing this. You simulate again another uniform random number, independently of the previous one. You just go on simulating independent uniform random numbers, and each time, if the random number is less than half, you go towards +1. And if it's bigger than half, you go towards -1. And at half, what you do doesn't matter at all, because this is, these are continuous random variables. But anyway, don't worry about it. You can just put half to be, on the either side, and you do the simulations. There's no problem. This will simulate a simple random. Okay, another question that was asked was that it's about this particular slide. We said that we should scale the time by n and the position by square root n, because after time n, the random walk will go up to square root n steps. It will grow in a square root n, of the order of square root n. What do I mean by that? Now, somebody asked, does it mean that there is some convergence or something? And I said, yes. So this relates to something called central limit theorem, which I'm deliberately hiding and putting under the carpet. What you can show is that the position of the random walk after n steps is Sn, right? If you scale that by square root of n, if you divide that by square root of n, the position is Sn. If you divide Sn by square root of n, if n is very large, this will converge to a known random variable called normal random variable or normal distribution. It's also known as Gaussian distribution. So since the position divided by square root n converges to a non-zero random variable, we say that Sn is going like square root n. If this is too technical, just think of it. Sn by square root n has some limit, when n is large, and therefore Sn is going like square. Okay, this was one question that was asked. Another question that was asked is that this is everything we are doing in one dimension. Can the same thing be done in higher dimensions? Say dimension 2 or dimension 3, etc. Which again I thought was a very good question. And the answer is yes. What can be done is that on each, so in 2 dimensions, you'll have 2 coordinates. On each coordinate, one can run a random walk independently of each other, and then scale each of them, scale both of them, okay, appropriately. And then what you get is called 2-dimensional Brownian motion. Similarly, you can do it for 3 dimensions as well. In 3 dimensions, you have 3 coordinate directions. Okay, so x-axis, y-axis, and z-axis, as we call it. So you just use these 3 directions, 3 independent random walks you run on these 3 directions. Okay, and then you scale appropriately in each direction, and then combine them. That will give you a 3-dimensional Brownian motion. Now, another question was asked is that if you do it in a higher dimension, do you have to divide by some other power of n, not square root of n? You have to divide by n power d by 2 or something if you are in d dimension. The answer is no. You still have to divide by square root n, because the whole system is growing in each coordinate of the order of square root n. So square root n is the right scale to do. Okay. So for that, one needs to use, again, multivariate central limit theorem, but I don't want to get into that. But the point is, this theorem that I mentioned, central limit theorem, that tells us that in each coordinate, the growth of the random walk is of the order of square root n. So dividing by square root n is the right thing to do. You do not have to divide by anything else. Okay. And then there was one more question that was asked, is that what if this random walk is not simple random walk? Say it's a biased random walk. So your coin is not fair, and then you have this random walk. So from 0, the person is going to 1 or -1 with probability say 60% and 40% respectively. And if you do that, and then you divide by n and square root n as before, will the Norbert-Wiener's result work, and will it still simulate the Brownian motion? The answer is yes. Even for any other random walk, any other reasonable random walk, okay, this theorem will be valid. Say, for example, if the random walk is biased random walk, in other words, same thing, except that the coin is biased towards either head or tail. So more often you take the +1 step than the -1 step. Then also the coin, then also this theorem will work. Only thing what may happen is when the coin is fair, typically it becomes Brownian motion very fast, as we saw from the pictures. Even in n equal to 1000, it looks like very jittery. It's already Brownian motion. At 10,000, surely so. For other values, for other coins, when the coin is biased towards either head or tail, this will take a bit longer time sometimes, but it will still converge to Brownian. Okay, so you can still use simulation. And there was one more question asked about in general about simulations. It's about modeling and simulation. And then let me repeat that question. So that question was, so you have a model, right, that you use, which basically represents the real world phenomena, some mathematical model that you have. Do you use simulation to validate whether your model is correct, or you assume your model is always correct and then you simulate to predict events in the future? This was the question that was asked. And my answer is that, yes, actually, we do both. Okay? So it's not like we do one of them and we don't do the other one. We do both. So in other words, we propose a model that sort of validates the data. Okay? And then we use simulations to cross-validate this proposition, whether this model is correct or not. If it is correct, we move on and then use simulations to predict future. Okay? What happens in the future. Or if the simulation results show that, okay, even though this was, thought of to be a good model, it looks like this model doesn't fit this phenomenon. Then what you do is you go back and try to check from the simulations what went wrong and adjust the model accordingly. And then you start from there. So you do both. You do both cross-validation as well as prediction. Both are important features of using simulation. Important applications of simulation, not feature. Important applications of simulation. And then there was one. I think there was one high energy physicist, and what she mentioned is that this is very much done in high energy physics, and many times they cross-validate a model, and then if it's not good, they propose a new model, and then they use simulation, etc. And there were quite a few people in the audience who use simulations, and they mentioned that this is done in their field as well. So there are various scientists in the talk, and this is how we concluded the talk. So okay, so thank you very much, and I'm done.